Hello, welcome to IPDay's Wednesday webinar. Today we're talking about the Essential Algebra Skill 2 of 3. We're talking simplifying. So don't worry if you weren't here a couple of weeks ago when we talked about substitution. You won't be behind. We've still got lots of great stuff to learn. And next week we'll address solving. But today we're already going to start comparing simplifying and solving a little bit because it's important to understand the distinction. So here we go. My name is Kate Redman. I'm an IPDay subject matter expert. It's my second year working with IPDay, and it has been a blast. I love doing these webinars, getting to do trainings. Just got back from Florida, in fact. I'm also the founder and CEO of Light and Salt Learning. And what we do is we make educational resources for adult education students and their instructors, especially for struggling students. That's kind of my jam. Today, if you have a question, you can actually type it into chat. I've got chat open. Certainly, you could use the Q&A as well, but and your microphones are all going to be muted. You're in listen only mode, and we are recording this presentation. It's going to be up on the IPDay website within 48 hours. The PowerPoint and the handbook that are related to this are already up there in your IPDay portal. You can access them there. Goal today, we're going to talk about what it means to simplify. We'll look at some student weaknesses with simplifying and how we can then connect it to our students' prior knowledge and connect it to their lives, as well as make sure that we use very clear language when discussing these mathematical terms and make clear distinctions between combining and multiplication division, as well as simplifying and solving. All right, so let's get to it. First thing, what is simplifying? So to simplify is to find the most compact equivalent form of an expression. It's what you guys generally think of as just doing the math. So for example, if I had an expression like 2 times the quantity of 5 plus 3, and I started going ahead and obeying those operations and making this sucker simpler, like doing the 5 plus 3 is 8, and then doing the multiplication there that's implied by those signs, 2 times 8 is 16. I've just simplified this expression, and now it's as simple as it's going to get. I can't get any simpler than a single number. All right. A few things to remember that are someone is saying they're hearing two voices. Joe can handle it. Okay. So a couple of important things to remember about simplifying. First, it's what we do to expressions, not equations. We're not simplifying equations, we're simplifying expressions. It obeys the operand. Hopefully, you guys know what I mean when I use that word operand. I'm just talking about the operation symbols like plus, minus, multiply, divide. When I'm obeying the symbols that I see, doing what I've been told to do with those symbols, then I am simplifying. That would be the opposite of solving. Think about when we solve, we use inverse operations. We do the opposite of what we've been told. And then simplifying obeys that order of operations, which I'm sure that you guys are familiar with, but we'll look at that a little deeper. But it's when we're simplifying that we're obeying that order of operations. Okay. Now, simplifying is one of the sub-skills of solving multi-step equations and inequalities. So when we're going in and solving multi-step equations, like for example, if we had 2x plus 5x equals x plus 17, there is a beginning step here that one of the first things we would want to do then is simplify the left-hand side. And so I said, what do we simplify expressions? We don't simplify equations. Well, what is an equation? Equation is just an expression equal to another expression. So no, we don't simplify across an equal sign. We're not going to, for example, bring this x in. However, we can simplify each one of the individual expressions on the left or right hand side separately, if possible. And so it's super important that students really, really are clear on when they're simplifying and when they're solving in order to get to those style of problems that are on the GED where they have to be able to solve 4 and 5 step equations and inequalities. I often say that simplifying is your first priority. I tell my students we pack before we move. So we clean it up, we neaten up the expressions on either the left or the right hand side before we start moving across that equal sign. And simplifying is done one expression at a time. So just the left hand side separately, just the right hand side separately. Let's look at some student work here to try to figure out what went wrong. So now I'll pull up my chat. Beautiful. And we're going to look at identifying weaknesses with simplifying. So here's an example of a student's work. And my question to you is, what went wrong? No, wait, you can type it into chat. What aspect of simplifying went wrong for this student? Beautiful. I see -6 should be -6x. Didn't put -6x. So that's an issue with what aspect of simplifying? Multiplying, absolutely. Amanda says didn't FOIL correctly or didn't multiply binomials correctly. Yes, FOIL is an abbreviation we use for that. And then once they did that multiplication wrong, of course, then they started collecting the wrong terms to be like terms. Nice job, you guys. Strong work. Next one. Okay, so this is another example of a student's work. Sorry, I tried to make it as clear as I could. The picture the student had taken wasn't great. But the purple is the student's original work here, and the red is their correction. So ignore the red for now. My question to you is what went wrong before they corrected it? Any thoughts? I see her student did FOIL wrong, but rather than saying they did it wrong, like specifically what happened, you might have been referring to the last one, but still. Maybe they did 6p minus 2 and got 4p, possibly. By the way, if you simplify it out, and you get the middle terms -12p and +16p, you do get +4p. So I think their +4p was correct. I think that their main mistake is not having that -4 or that -4. Exactly. They forgot the last portion, -2 times 2, Christopher. Yes, absolutely. I think they forgot to fully complete the act of multiplication, the way that multiplication passes out or distributes from every term in the first grouping to every term in the second grouping. Lovely. Thank you, guys. The same student also did this work. So again, we're just looking at the purple. You can ignore the red, which is their correction. But looking at the two purple lines, they multiplied out and then they simplified. What went wrong here? Yeah, this one's interesting, isn't it? I've used this many times and I don't know if they forgot the last part. I'm not sure what we mean by they forgot the last part. They combined unlike terms. Megan, I think you're right. I think they did combine unlike terms. Yeah. How did they get 13n to the third power? What happened there? Definitely we see there being some combining of unlike terms here, and we know when we're supposed to be adding and subtracting, we're not supposed to see the variable portion change at all, and yet this student is struggling with that, which is interesting because they did many other problems correct. I'm not sure which one, why this particular one stumped them, but all of a sudden it's like they lost their algorithms. All right, here's another student error. So in this case, they're solving multi-step inequalities, but this student made errors related to the concept of simplification. Any thoughts? Yes, Kim, absolutely. People add 2n and 12n and get 14n squared. Mhm. Yeah, someone says looking at number five, they subtracted 3x, but then they also subtracted 3. Exactly. That's not balanced if you subtract 3x and 3. Oh, we also see that there um, could have simplified that 3x plus 5x right from the start and didn't. Beautiful. And then for number six, they added 7y. Cecilia says, yeah, absolutely. I mean, I suppose you could add 7y, but that's not what you'd get. You wouldn't suddenly blank out, of course. If we had 7y and we added 7y, we'd get 14y. Wouldn't be super helpful, but it could be done. So nice job, you guys. All right, and here's my favorite. So the great thing about this one is it's not actually wrong, by the way. This student got a correct answer after all of this work. But does anybody have anything to say about their, uh, just about what happened here? Interesting technique, right? Yeah, they could have saved so much time and effort if they'd have just simplified the left and right hand side before they began. But instead of doing that, wow, there was a lot of moving around one term at a time. And just very interesting work. At one point, they did decide to simplify, but then they moved some more. Yeah, I'm not saying that this student is wrong. I definitely would not tell this student they were wrong. I would commend this student for their good logic, but I would also show them a more direct route to where they were going and how simplifying, if they prioritize it before solving, can really make their lives a lot easier. Okay, nice job, you guys. Thank you. Um, oh, someone says they think Einstein was sloppy. I imagine that he was based on what I've heard of him, but I didn't get to see his work. Okay, so but sloppy and inefficient are kind of different. I don't know. But that being said, there was a lot of chance for that student to make an error coming back to that with how many steps that they turned this into. So again, I would commend them for their good logic, though. So I think one of the things that's super important to do with students is connect our algebra to our arithmetic, connect to our prior knowledge. Too often, students think, oh, we're doing something new when we get to algebra. So I would like to insist that we've always looked for like terms. I know we're talking about when we start adding and subtracting in algebra, we start talking about combining like terms. And students tend to think that this is the first time they've seen something like that. But no, actually, we've combined like terms from the very first, from the start of math. So think about it. Okay, you guys, how would you line up your work to add 837 and 24? If you were doing it by hand, just briefly in the chat, humor me, I do this with students all the time. How would you line up your work? I love this. Usually people tell me do it on the right. And so then I have to tell them, I have to ask the question why. But you guys are got right from the start are telling me we line it up by place value. Beautiful. I love it. Absolutely. We line up ones with ones, tens with tens, hundreds with hundreds. We are always have always been combining like terms, the same kinds of things since the beginning of math. And so then it makes sense if you think of it that way, why we go up to this. Now, you guys already kind of answered the question, but I'm going to go to what students usually tell me when I ask them, how would you line up your work to add 8.37 and 2.4? And they always tell me, line up at the decimal, which I agree with. Of course, we are going to line up at the decimal, but the question is why? Why do we line up that way? And that's one that often has students stumped. So I'm excited to see that you guys already said line up by place value, line up by place value. because I want your students to know that as well. They should know that they're combining like terms right from the start. All right. So, and then another question to ask students, which one of these is easier for you to do? And of course, we know that a student would much rather add 1/5 and 1/5 than 1/4 and 1/5. But the question, of course, again, is why? So why is it easier to add 1/5 and 1/5? Yes, they have a like denominator. And so what does that mean? Like, what does that mean to us? Why does that make it simpler? It's basically the same units. It's the same type of thing that we're adding. We're adding fifths and fifths. Just like we could add ones and ones or tens and tens, we can add fifths and fifths. Nice. Beautiful. So it's not only addition and subtraction that is carrying over to the world of algebra. Multiplication always carries over. You know, we often teach distribution like it's just a lesson one day. Oh, when I say the word distribution, you usually think I'm talking about multiplying something like 3 times x plus 7. But the fact of the matter is, we've been distributing ever since we've done multi-digit multiplication. As you know, guys know, when you go to multiply, what do you do with the digit? You just pass it out. Do your students realize that that's what we're doing? We're just doing 8 times 3, and I'm going to write it slightly differently. Not that you can't write it the standard way, but do they know that they're doing 8 times 3 is 24? That they're doing 3 times not 5, but 50 for 150? That they're doing 3 times 700 for 2100? And 3 times 6,000 for 18,000? Now, of course, this is not how we line it up. I know in the standard algorithm, well, in some countries they do. But the point being, do they realize that since the beginning of math, we've been passing out multiplication and then combining like terms, ones with ones and tens with tens, and so on and so forth. And hopefully I did that one right. One of my favorite things to do is make errors while you guys are watching me. So now, I carry that through to when we're multiplying by multi-digits. Think about what we do again. We pass out each digit of the first. Sure does remind me of doing something like 2x plus 5 times 3x squared plus 5x plus 6. It's that same idea of passing out, passing out, passing out. So this is nothing new here. And even division passes out. Think about that long division algorithm as we move down that number. And so we've always distributed or passed out in multiplication and division. Beautiful. And another thing is we're still following the order of operations. Okay. I'll slow down because this is one of my pet peeves. I'll hear teachers say, or students say, I should say more often, that we're doing order of operations problems right now. And I'm like, what's an order of operations problem? The order of operations is like saying that you have a gravity problem because order of operations is just how the order in which we simplify. It's a big overarching rule that doesn't only certain come up on certain problems. And so I just think it's interesting language. But either way, what we're doing when we say we're doing order of operations problems is we're simplifying expressions. And whether that's arithmetic expressions or it's algebraic expressions, we're still going to follow the same order of operations. So this was a really exciting day to me, the day that I realized that the order of operations really only follows two rules. I know people will shout, PEMDAS! PEMDAS is not my favorite way to remember the order of operations, but any way you remember it, there's just two big overarching rules. The first thing is that we move inside groupings to outside groupings. Math is an inside to outside language. It's a nesting language. So innermost to outermost. And then the second big overarching rule is that we move the highest order operation to the lowest. And when I talk highest order, it's almost like the order in which we learn them, right? So first we learn to add and subtract, then multiply and divide. Then we learn about the exponents and the roots. And when we go to work them, we work our highest order operations to our lowest. So think about that order of operations. You do exponents before multiplication and division before addition and subtraction. Now, my favorite way to sum that up, like I said, is not PEMDAS. It's the same thing the National Council of the Teachers of Mathematics uses, which is GEMMA. So just taking a look at this, I start with G, GEMMA being, or G, sorry, meaning inside of groupings. So starting within the innermost groupings here, which yes, in this case happen to be parentheses, but aren't always parentheses, which is why it's important not to use that language for just parentheses. So, or use the P for parentheses. All right, so 11 minus 7 is 4, 3 minus 1 is 2, and I'll drop everything down. And this is how I would demonstrate it with students as well. Next thing, of course, our next highest order of, or our highest order of operations that we know, our highest order operation. You guys, hold on. Okay. The highest order operation we have in this problem here is exponents. And so I'll do my exponents next. That's the E in GEMMA. And so 4 squared is 16. 2 cubed is 8. And I'll drop down everything I haven't used. After exponents comes M for multiplication and its inverse division. Notice that I pair them together. So 3 times 16 is what? 48? Plus 5 times 8 is 40. And now finally I can do my addition or subtraction. And addition and its inverse subtraction. And so this, the more compact we can be with rules, the better off our students will be. So I like that summation of GEMMA better than PEMDAS. And like I said, so does the National Council of Teachers of Mathematics. All right. Beautiful. Okay. Woo. Now, we don't just need to connect to what our students have learned before. We know some of our students have gaps in their learning, but we can also connect our algebra to the real world. And I think this is probably the most important thing we do in math class. Oh, shoot. I had such a good question. I'm going to back up. Okay, so somebody asked me what other types of groupings they can be. Well, of course, we can group things within brackets as well, but beyond parentheses and brackets, you can group in all kinds of symbols. Like, for example, a really common GED style problem that they talk about is with distance. And the distance formula between 2 points is A minus B, the absolute value, though, of A minus B. And I would go inside to outside in that case. I would start with A minus B, and then I would take the absolute value. I would make my answer positive, basically. So that right there says subtract and make your answer positive is one way to think of that. Or inside of radicals, think about we have formulas when we start talking about the distance formula or the Pythagorean theorem, we get things that look like that. And now we're working inside of radicals before we hit anything on the outside of it. So anyway, lots of types of groupings. Okay, lovely. Thank you. Good question. Pay attention to the chat quicker now. So anyway, one of the most important things we can do is relate to our students' real lives. So talking about like terms, that's a huge one. I love starting with my students with something really simple like apples and apples, or in this case, pears and pears. So I don't think there's a single teacher here who doesn't know what 3 pairs plus 5 pairs is. And our students are the same way. A simple question like this, even the least skilled students in the room can usually answer it. And then from there, I can jump to this question, which is a great, fun question to ask in a classroom. So I'll ask you guys the same thing. What is 3 pears plus 5 oranges? Imagine what your students might say to that. I love it. Kay says 8 fruit. And then other people say three pears and five oranges. Duh. Eight pieces of fruit, a fruit basket. Yeah, I love it. And so I love having that conversation with my students. Like, how come some of you could add and some of you couldn't? And of course, it's because some of you turned it into the same kinds of things when you said fruit, right? And said, one student said fruit salad. I love it. What a great conversation. Um, but we have even a level one student can understand this conversation. And so I like this, I would keep going with a lot of real world examples. If our students know anything, they know their money, right? So we can say, what is $3 plus $5, but then launch into what is $3 plus 5 cents. And of course, what is $3 plus 5 cents? It's $3.05, right? And then same thing, we could do it with measurements, feet and feet, down to feet and inches. And if you go through it this way, it is even a level one student can get to, well, then what is 3x's plus 5x's? Of course, it must be 8x's. And what is 3x plus 5y? Well, it's 3x plus 5y. And this is a great way to launch into this conversation and not just be like the rules are, which is a mistake when it gets to struggling students. They need to know where the rules come from. It's not just random rules, it's really the pattern of what happens in this world. And so it happens in algebra as well. So, and then again, we see multiplication and division distributing in life. So they don't just distribute in the classroom, right? So nice little, and by the way, all of these questions that I asked are all in you guys' handout that you can access through the IPDAY website. And so if you want to use them with your students, you can. But let's have a little problem here. This year, Jimena wants to bake goodies to give as Christmas gifts. She plans to make 12 baskets full of baked goods, each with one loaf of gingerbread, eight chocolate chip cookies, five butter cookies, and 2 cups of caramel corn. How much of each baked good does she need to make? And this is a really great way to launch into the fact that if she's making these 12 baskets and every one of these baskets has something, we're going to have to multiply everything by 12, the gingerbread by 12, the chocolate chip cookies by 12, the butter cookies by 12, and the caramel corn by 12. And then that's a beautiful illustration of why 12 times one loaf of gingerbread and eight chocolate chip cookies and five butter cookies and 2 cups. Oh, I should have used something besides caramel corn. Of caramel corn, we'll call it D, would pass out. And we can see that it relates right to the real world. And it's not just multiplication, of course, that passes out, that distributes. It's multiplication's inverse. If you know how to do an operation, then you understand its inverse as well. And we can see the other way around with our little gift baskets. But Felicity plans to give away gift baskets of fruit and nuts for the holidays as well. She buys 24 pears, 30 apples, 6 pineapples, and 12 pounds of pecans to assemble 6 gift baskets. How much of each item should she put in each basket? And we can see that same idea that we're dividing through. And that's a beautiful picture of why 24 pears plus 30 apples plus 6 pineapples plus 12 pounds of pecans, which are nuts, divided by 6. Oh, you guys, I used P 3 times again. So struggle. We'll call that one Q. Why that one would divide through and pass out that way as well. So lovely. Okay, now it's super duper important to use clear academic terms when you are talking about algebra. Students mix them up and teachers mix them up as well. So this is a big issue I've seen. I think mostly because a lot of GED teachers, they're not math teachers by trade. They get thrown into teaching math. There's always a shortage, or they've been K-12 teachers where the algebra is not as important. And so it's really important to use accurate academic language. So let's look at a few of my pet peeves. No, a few of the keywords that you should be using repeatedly and frequently. Your students should know what they mean. So the first one is simplify. We already talked about that. But to simplify there is to obey the operands obey the symbols to create the most compact form of an expression. I did get in a debate and I don't have the answer to it. So if you're a math major and you want to debate with me, oh, so wait, let me finish what I'm writing. Most compact form of an expression. Okay. So I did get into a debate one time with someone about whether 2 to, let's say, a power, so 2, 4, 8, 16, 32, which one, 2 to the fifth power or 32, is more simplified. So I will allow for you guys out there that sometimes some mathematicians will say, especially when it gets to the bigger numbers, right? As we start getting larger, 5 squared is 625. There's an argument that this form is simpler than that form. But that's not an argument we need to have with our students because it would specify if our students needed to have it in exponential form. So if you're one of those teachers who wants to get into that argument, I don't have a strong opinion on it, okay, you guys? But oh, Kim, that's a good rule of thumb. I love it. And again, this is not a hard and fast rule. This is just, I think that this is Kim's opinion on what's simplest here. But she says if the base is under 5 and the exponent's under 5, it's better to just multiply it out. Whereas if it gets higher than that, it's simpler to leave it in exponential form. But either way, that sounds like a nice rule. Yeah, see, Caitlin, it's a good discussion, isn't it? But it's not really one we have to get into with our students because they would definitely clarify whether it was on the GED or it wasn't, if it was in college, if they wanted something written in its exponential form, they would get just directly told. But definitely a good conversation, a fun one to have. Okay, so next one, an expression. What is an expression? And this one's super important. This is my big, big, big pet peeve because expression is the one that's instructors will call equations and students will call equations. And it's really important that we call a spade a spade. We call an expression an expression. So, what is an expression? It's a single value, not a single number necessarily, but a single value that can be represented by any combo of numbers like 7, variables like x, and or operands. So operands again are just those operational signals, symbols like plus, minus, multiply, divide, yada yada. Lovely. So you can have really simple expressions like the number 7 is an expression. It can get more complex like 2x plus 1, or it can get really ugly like, 3 negative 3x to the third power y squared. Either way, um, any one of those are an expression. They represent a single value. All right. And totally cool to point out that it does not have an equal sign. Exactly. It's once we bust out, although, I mean, you know, I know I'm being a little, what's the word, pedantic when you're getting caught up in language, but I'll give you an example. Here's an expression, 2x plus 5x. A mathematician would write the next line with an equal sign, equals 7x. And yet, what do we have here? We do have an expression and another expression. And so it doesn't have a relationship. We don't have that relationship of equality. So it's not two-sided. So I know what you mean by does not have an equal sign, and I agree with what you're trying to say. But just to clarify, so nice job. So that's an expression. Now, combine, the word combine. When we talk about combining, what are we talking about? We're talking about addition and subtraction. As we know, once you bust out those positive and negative numbers, the line between addition and subtraction really blurs. And so we begin to just call it all combining. Distribute is the way that multiplication and division pass out to every term in a grouping. Okay, so that being said, like if I was multiplying 2 times x cubed plus 2x squared minus 11, terms are things that are adding or subtracting, which is one of my next definitions. So if I have these three terms here, these three things adding and subtracting, my multiplication will pass out to every term in my grouping. Beautiful. Coefficient. What is a coefficient? When you look at I probably did these in the wrong order. Let me do term first. So term, the term is the portion of an expression that's adding or subtracting. Okay. And I wanted to do that one first because what is a coefficient? A coefficient is the number portion of a term. So for example, if I have 2x cubed minus 4x, we have two terms, term and a term. The number out front is the coefficient. So the coefficient of this first term is 2, and the coefficient of this next term is negative 4. And why is this important? This language we should be using all the time in our classrooms. Now, obviously, we want to pair it with common language. So I will often say the coefficient, the number out front, the coefficient, the number out front. I, in fact, almost always say both because I want my students to have that definition, but I also want my students to have that academic language so they're prepared for college. Okay, lovely. I think you guys already know what the variable is, but the variable is a symbol, usually a letter. So it's the letter portion of our terms. Beautiful. And it does represent an unknown. You can say that it represents an unknown quantity, but a variable can also represent any quantity. So for example, in 2x plus 7 equals 11, it represents an unknown quantity. But if I just say 2x plus 7, now it represents any number. For any number x, you multiply by 2 and you add 7. Or if I write something like this, 1 times a number is the number itself. Now I'm saying for any number. For any number a, if you multiply it by 1, you get the same number. So beautiful. And then finally, I want you guys to use the word factor, both as a noun and as a verb. So that one comes up a lot on the GED. And so important that they understand it. So what is a factor? It's the part of the expression that's multiplying when you're looking at terms. I think I had too much coffee today, guys. I'm moving too fast. I should slow down. So the part of an expression that's multiplying when you're looking at terms. So 2x squared, for example, plus 3x to the fourth power. Here's a term. So this term has actually three factors. It has a 2, and then it has two factors of x multiplying. And this is an important word to understand because numbers are really constructed of their factors. They're built out of factors. And even when you understand that, whether it's in the world of algebra or if it's in the world of just thinking about, like, for example, the number 20 is made of certain factors. 4 times 5, 2 times 2. It's made of the factors 2, 2, and 5. And that really controls how it behaves when we're multiplying, dividing, when we're using it in all sorts of aspects in mathematics. So understanding a number's factors is important. Okay. And then to factor as a verb means expanding an expression into its factors. Okay. Woo! That was a lot of language I just threw at you guys. Rude. But these are some terms here that I would like you to be using in your classrooms, and I would like you to be using them accurately. So, taking the time to understand these terms, even if you wouldn't teach it to students this way 10 at a time, but you should be using these accurately in your classes. Okay. Now, we use a lot. Kim, when you said, can you say the number in front of the variable? I bet you were talking about then the coefficient, and that is exactly what I say. The number out front or the number in front of the variable is the coefficient, and that's a great way to say it. So that's a perfect launch into the memory phrases. So we use memory phrases all the time in the GED classroom, and I think they're super helpful. I think they're super useful. I want you to be using them. Like here's one that I say all the time. And when I tell my students, talk to my students about adding and subtracting, I always say we're adding and subtracting the same kinds of things. But it is important to pair that with its academic language. So you guys told me earlier, like we are adding and subtracting the same place values. Or you told me that we added and subtracted with common denominators. Or we talked about adding and subtracting with like terms. So these are all the math phrases for them. So obviously your students need to have both that simple language, that simple idea, the same kinds of things, but then paired with that academic language. Beautiful. Here's my big pet peeve. Oh, and you guys already, two of you guys said it. Don't feel bad. You didn't know this was coming. Foil. Guys, foil is not a verb. Foil is a mnemonic that helps us remember how to do what? What are we doing when we say foil? Anybody? Foil stands for first, outer, inner, last, but still, what are we doing with it? We're distributing something, we're multiplying. So in the case of foil, what are we distributing? We're multiplying two binomials. It's a way to remember how to multiply binomials. And yes, people do say F for first, meaning the first term times the first term, and then O for outer, meaning the outer term times the outer term. I for inner, meaning inner times inner, and L for last, meaning the two last terms are multiplying. But that being said, what are we really doing? Yeah, we're distributing. We're distributing every term in the first grouping to every term in the last grouping. All we've ever done in mathematics is when we multiply is distribute. That's the way it works. So nice job, you guys. So by all means, you can tell your students we remember how to multiply binomials using FOIL, or let's remember to distribute all the terms using FOIL. But what are we doing? The students need to know we're not foiling, we're multiplying. All right, beautiful. Yeah, Harold says FOIL is just distributing twice. Absolutely. And just like when we were multiplying with multi-digit numbers, at the end, we then combine what we have that's like. Beautiful. And then another thing is I'll use the term pass out paired with distribution. I just need to pair it again. I can say pass out, but I need to pair that with that academic language of distribute. So we pass out, we distribute. Okay, lovely. Lovely, lovely. So in using that terminology accurately, some commonly misused words include expression versus equation versus inequality. Super important that we are calling them what they are. And in that mode, we are accurately saying what we're doing. So we simplify expressions, but we solve equations and inequalities. We don't solve expressions, you guys. It's just so frustrating to me when I see things like this on a piece of paper. It's no wonder our students are confused. There's websites out there that call themselves GED prep websites that have stuff like that. Solve 2x plus 7x plus 5. Well, a poor student could sit there for 10 years. Beautiful. Good job correcting your students when they say solve expressions, because a student could sit there for 10 years trying to solve. They're never going to be able to figure out what x is in this case because there's no clue. We can't solve this. All we can do is simplify this. So solve and simplify with expressions versus equations, really important. That's actually, if you take nothing else away from the webinar today, Just students understanding the difference between expressions and equations versus simplifying and solving can make such a huge difference for struggling students. Okay. So yeah, simplify versus solve. Then we talked about combining already, meaning specific meaning of adding and subtracting. Um, I know. I was like, why did I include add and subtract when I already had combine? I know what I'm talking about. I'm talking about this. Okay. So when you're doing like negative 22 minus 43, what is that? That's subtraction, right? So I, but it's so funny because when I ask students how to do it, they tell me, I'm sorry. You guys, I'm stumbling all over myself today. When I talk to students about how to simplify this expression right here, negative 22 minus 43, and we walk through, oh, I'm already in debt, $22, and now I'm going down another 43, they say, oh, it's not subtraction, it's addition. And why are they saying that? Because they're thinking about doing their side work, and if they wanted to, then they could combine the absolute values of 22 and 43 since they're both negative in using addition. But then the students are confused. Is this a subtraction problem or is this an addition problem? And so I would just encourage you to talk that out with your students. No, we're not adding those numbers, although one of the methods to find the answer is to add their absolute value. This is a subtraction problem. All right, this is I shouldn't say subtraction problem. This is a subtraction expression. Okay. Um, so now, after we make sure our language is in place, we have to make sure that a student has a really clear line of when they're combining versus when they're multiplying and dividing. And we're going to see, I mean, we already saw it with our students before that this was a huge issue, when that student who had 13n, I think 13n squared. Oh no, they had 12n squared originally plus 1n, and then they said 13n to the third power. So this student is mixing up rules, as we would say it, between addition and subtraction and multiplication and division. But that having that clear line is what's really going to help students from making those mistakes. So students will confuse the rules of combining like terms. There's the one we were just talking about, with those of multiplying and dividing. And so how can you tell that students are doing this? They're combining unlike terms. They're dropping variables, letters just drop, or they're adding exponents when combining. If they're doing that and you see that, then the important thing that you need to do, that distinction you need to make is, do you know when you're multiplying? Do you know when you're adding or subtracting? So when we go to distinguish for students, here are the big main things to point out. Okay. When adding and subtracting, that's when we combine like terms. When multiplying and dividing, we distribute, we multiply with polynomials. Adding and subtracting can only happen if those terms are like. So we talked about this already. 4x plus 5x we can add. But 4x plus 5y we can't make any simpler, nor can we with 4x plus 5. Now, multiplication though, you guys, sometimes I say addition and subtraction is like the army. Everybody lines up, they're all with their own kind. But multiplication and division is very hippy dippy free love. Everybody, it just passes out. Everybody can multiply with everybody else. So whether it's x's and x's, we can multiply 20 and then have two factors of x. Or x's and y's, we can multiply 20 and then have a factor of x and a factor of y. Or, of course, if we just have numbers with a variable, we can combine. So anybody can multiply. When you're talking about adding and subtracting, each term is only going to add a single time, again, with its like. So we only see that happening once. Whereas that multiplication distributes or passes out, we use terms over and over again. So we see that repetition there. And when adding and subtracting, only coefficients change. That variable term is never affected. Whereas with multiplying and dividing, we see new types of terms being created when those variables multiply together. So we go from having an x uh, term, I'll say, and a y term, and we multiply them together and we get a 3xy. Whoa. sorry, 6xy. But we see a new type of term created, an xy term, whereas that never happens, of course, with addition and subtraction. We'll never see our variable portion affected. We just add that the coefficient, and that variable term stays steady. So I know you guys know this, but these are the distinctions that we need to be able to make for our students. And by the way, I have videos linked in the handbook again that really go through the distinction with students about multiplying and dividing versus adding and subtracting so they can get a similar clarification in their heads. So what's our fix when students are mixing this up? Our fix is to read expressions aloud and require students to do the same. A lot of these errors are happening because they're just memorizing the way based on the way things look. And so by reading it aloud, you're going to end up reading the operands, the addition, subtraction, or multiplication, division, and that can help students really know what they're doing. And we can do that each step of the way. Read each resultant expression aloud. Important to, yeah, I we don't do that enough. I'll slow down. Someone said it's a really good point to say it out loud. We really don't do that enough in our classroom. We have a tendency to teach reading and writing expressions like it's a single lesson instead of teaching algebra like it's a language and something to do every single time we have algebra. We can be reading it aloud. I like there's a game that I have that I play with students or instructors called Algebra Telephone that we can practice with, but we can also just practice by just instead of always writing the problem on the board, do you ever verbally give a student a problem? Do you ever make them verbally give it to you? And that's just really good practice to do every time. So have students identify the operation before they begin. Like, what are you doing right now? Oh, I'm combining like terms. Well, what does that mean? Are we adding, subtracting? Or are we multiplying, dividing? Um, and so just being really clear before they even begin which one they're doing will help them to start remembering which is which. And then, of course, we need to have our days where we isolate skills. I know we all isolate skills, right? We have one day where we're doing distribution. We have one day where we're multiplying binomials. We have one day where we are combining like terms. But it's important to get to the stage then where we mix it up. So I would encourage you, I teach it in 4 lessons. So I do a combining like terms. Then I do a review of the exponent rules. So they're basically just multiplying monomials, but if they whether they realize it or not. Like, for example, 2x squared times 3x. So I do a day where we're just multiplying monomials and with a review of the exponent rules. And then from there, then I do the straight distribution where it's just a single term like 4x multiplying by a grouping like 3x minus 1. And then finally, I get to the day where we're multiplying polynomials. And yes, that mostly consists of binomials. But for my more advanced students, I'll have them bust out a few binomial times trinomials. But anyway, I teach that in 4 lessons, and then we have a day where all we're doing is just simplifying all mixed up. Because any one of those they can master on their own, but this is the hard one. When it's all mixed up and we're trying to keep track of all the rules at once, man, it's such a jump for students. So I think that it's important that we get to the stage where they're alternating, they're going back and forth, and it's mixed, and they're really getting in that practice of knowing which skill to pull when. Uh, yeah, so beautiful. And we always give our students verbal prompts, right? We'll help them when they start getting lost. So I would encourage you to have your verbal prompts focus on why, not what. So if you have 7x plus 3x, it's not like, remember, add the numbers and leave the x the same. I'll often say something to my students like, you have 7x's and you add in 3 more x's. How many x's do you have now? Saying it like that really reinforces the idea of these are just behave just like apples and oranges. Or, for example, the exponents tell us we already have two factors of x. 2x is multiplying. Now we're multiplying in three more factors of x. How many total factors of x are there now? So, right, exponents count factors of x. Okay. We are running out of time a little bit, so I'll just go through this quickly, but also draw a really clear line between simplifying and solving. So students will often mix up the rules of simplifying with those of solving. So signs of that include using inverses when they should be obeying the signs, trying to balance an expression. We see them doing the same thing twice to an expression, or dropping or ignoring equal signs or other relational symbols. So this student, I had to copy their work because it wasn't super legible. So this is my handwriting, but I promise this is student work. Um, had an interesting time of doing all of those things. It's like they didn't understand that equal sign at all. And then, of course, simplifying across the equal sign is a big issue. So just, we already kind of went through this, but distinguish to your students that simplifying is done to expressions, solving is done to equations and inequalities. Simplifying is one-sided, one expression at a time, where solving is two-sided, or even three if we look at some compound inequalities, and it balances every expression. Simplifying obeys the operands. Solving uses those inverse operations. Simplifying follows the order of operations, and solving reverses the order of operations. Did you guys know that? That's when you start omegging. You go backwards. Simplifying reads top to bottom. We always simplify underneath. And then solving is when we start crossing that equal sign. So we're going to emphasize the extreme importance of equal signs and inequality symbols. Emphasize the importance of maintaining the relationship between expressions. Insist on students simplify from top to bottom, not jump equal signs. So, like if my students are doing a order of operations problem, they're simplifying down the page, I actually will correct a student who comes and jumps up here and throws the answer up top right. I'm like, that's not where I was expecting to see the answer. We simplify top to bottom. Uh, you know what? The three wisdom principles of solving, I'll get into it if you join me next week. Next week's webinar is on that. But do help them to distinguish between the left and right-hand sides of an equation. I will often have my students put a line through the equal sign or even block one side or the other with a piece of paper to check if each side is simplified. All right, it's all a recap, but we're running out of time. So time to give IPDAY your feedback. They'll put a poll up on the screen and you guys go ahead and fill it out with your feedback, all right? Um, And then there are two different webinars next week that you guys can join us at. So on Tuesday at 1 p.m. Eastern Time, they're doing a Tech Tuesday webinar, integrating financial literacy with AI and web-based tools. And then on Wednesday, the Wednesday webinar at 3 p.m. next week, March 11th, is Essential Algebra Skill 3. We're going to finally talk solving. Yay! So that'll be with me if you're interested. And I hope to see you there. Thanks for coming.